Joseph Rudnick. I'm the Interim Dean of Physical Sciences, and it is my privilege and my pleasure to introduce the speaker at today's UCLA Science Faculty Research Colloquium. This ongoing lecture series showcases the exciting work being done by our faculty across the campus. It's sponsored by the Division of Life Sciences and the Division of Physical Sciences in our UCLA's College of Letters and Science, with the participation of the Schools of Medicine and Engineering. And it's made possible by the generosity of SL and Betty Huang. Okay, so now the introduction. Actually, a very smart man who is coincidentally my father used to say that the secret to giving a standing room only talk is to arrange to have it in a small room. Actually, in this case, even though we chose a much larger venue for this talk, you can see what the turnout has been. And that's actually no surprise, because the speaker today, Professor Terence Tao, is the equivalent of a rock star in mathematics. His talent emerged early on in life in that he began taking college courses at the age of 9 and was earning medals in international competitions at the age of 11. Immediately after earning his PhD at the ripe old age of 20, he came to UCLA and 4 years later was promoted to full professor. Terry's work has earned numerous honors, and I'm only listing a few. He's been a Sloan Fellow, a Packard Fellow. He's won a fellowship from the Clay Mathematics Institute. He was just awarded a MacArthur Fellowship, the so-called Genius Grants. And of course, this year, he was awarded a Fields Medal, colloquially known as the Nobel Prize of Mathematics. The citation for that medal is for his contributions to partial differential equations, combinatorics, harmonic analysis, and additive number theory, 4 distinct fields in mathematics. He's been called the Mozart of mathematics, but to my mind, it's actually more useful to refer to math's own prodigies in terms of the number, the range, and the impact of his contributions. Terry invites comparison to Carl Friedrich Gauss and Leonard Euler. He is, in short, the genuine article. Today, Terry will be telling us about structure and randomness in the prime numbers. Terry. Thank you.
Thank you very much. Nice introduction, Joe. It's good to actually speak in my home university for a change, even if the weather isn't quite what I remember it to be. But anyway, so I'm going to give a talk, not so much on my own work, actually, but on a field that I work in, number theory, one of the 4 fields Joe mentioned. So number theory, and specifically in the study of prime numbers, which is a very significant slice of number theory. And this is a very old topic. 2,000 years of research has gone into this topic, and I'm not going to talk about all of this in 1 hour. So just a whirlwind tour, so the equivalent of going through, Paris and just seeing the Eiffel Tower and the Arc de Triomphe, and so forth. But not really giving it's impossible to give more than just a taste of the type of things that are going on. But I just want to convey that this is a lot of work has gone into this. We know a lot more than we did 2,000 years ago, but there's still a lot more to be done, and it's still a very exciting field with lots of discoveries, every year, basically. So we're talking entirely about the prime numbers, so you all know what a prime number is, so just review the definition. A prime number is a natural number larger than 1, which cannot be split up as the product of 2 smaller numbers. So 2 and 3 and 5 are prime, but 4 is not, because 4 is 2 times 2. There's 20 or 30 prime numbers here, and so there they are. So why do we care about these numbers? Well, one way to think about them is that they're sort of the analog of atomic elements in chemistry. They're sort of the fundamental building blocks of multiplication in the natural numbers. And this comes from one of the first theorems about primes, dating back to Euclid, 300 BC, which is a fundamental theorem of arithmetic, that any natural number bigger than 1 can be expressed as the product of 1 or more primes. So it's just like every molecule can be expressed in terms of atoms. Every natural number can be expressed in terms of primes. And furthermore, there's really only one way to express each number in terms of primes, other than the trivial thing of being able to rearrange the product. So for example, the number 50, you can split up into the primes 2 times 5 times 5, or 5 times 2 times 2, or 5 times 2 times 5. But there's no, other than this trivial rearrangement, there's no other way to express 50 in terms of primes. But the reason, so this theorem is so important, this is the reason why we don't consider 1 a prime. So I mean, 1 can't be split into smaller numbers either, but if you made 1 a prime, then the fundamental theorem of arithmetic wouldn't be true. And we really want this theorem to be true. So we do not grant 1 membership in the primes. Okay, so this is the first reason why primes are important. And after this theorem, the first really interesting theorem about the primes is that there's lots of them. So the first theorem is Euclid's theorem, also due to Euclid, that there are infinitely many prime numbers. So unlike atomic elements, of which you only have 126 of them or so, we actually have infinitely many primes. And which is in sharp contrast to, say, addition. If you look at addition instead of multiplication, the only prime, so to speak, is 1, because every number is just a sum of a whole bunch of ones. But that's not the case for multiplication. So I'm actually going to give you a proof of this theorem. I know that this is a non-technical audience, and I'm not going to inflict any real mathematics, any real detailed mathematics on you. But this one proof is so beautiful that I think it just, and quite simple, that it has to be shown. So it introduces one of the best tools in proving a very unintuitive tool in mathematics, that of reductio ad absurdum, proof by contradiction. You want to prove something, well, pretend it's false, and then show that that can't happen, and then that indirectly shows that it's true. G.H. Hardy is a famous British mathematician. Once said that this is a finer gambit than any chess gambit or any gambit in any other game. So a chess player may offer you a rook or a queen, in order to win the game, but the mathematician offers the game itself, okay, and still wins. So, okay, so here's how the proof works. So you want to prove that there are infinitely many primes. Well, suppose there weren't. Suppose there are only finitely many primes. Then you could count them. You could call them P1, P2, up to Pn. So suppose, for example, 2, 3, and 5 were somehow the only primes in existence. Then what you do is you take all those primes, and you multiply them together, and you add or subtract 1. So you take 2, 3, and 5, say, you multiply them together, that's 30. You add or subtract 1, you get 29 or 31. So that gives you two new numbers, distance 2 apart, which I'll come back to later. And so these numbers, this pair of numbers, they're both larger than 1, but they can't be divided by any of the prime numbers that you already have. Okay, because 2 times 3 times 5 is already divisible by 2, 3, and 5, so if you add or subtract 1, they can't be divided by 2, 3, or 5. And those are the only prime numbers that are out there. So you've constructed some numbers which can't be divided by any prime number at all. And that contradicts the fundamental theorem of arithmetic, because that tells you that every number can be split into primes. And we've given you some numbers that can't be split into primes. So hence, you can't have finitely many primes. You must have infinitely many primes. So it's a very short proof. So it's very weird. It's an indirect proof. It tells you there are infinitely many primes, but it doesn't tell you where they are. It just tells you it really is only telling you that there can't be finitely many primes, so there must be infinitely many. And so there are some more direct proofs which more explicitly try to hunt for primes, but they're nowhere near as short or as elegant as this one. So we know abstractly there are infinitely many primes. We don't actually have a good way of this. I can't show you infinitely many primes. And in fact, we only know finitely many primes. And just to give you the world record right now, the largest prime that is actually known is that we can write down explicitly is 232,582,657 minus 1. So that beast is almost 10 million digits long, and it required a distributed internet project to show that it's prime. So that's the biggest prime we know of. So even though we know there's infinitely many, that's the biggest one we can actually write down. Okay, so in Euclid's proof, I took a bunch of primes, multiplied them together, and added or subtracted 1, and I got these new numbers, which differ by a factor of 2, differ by a distance of 2. So that suggests, defining a concept, we define a pair of twin primes to be a pair of numbers which are both prime and distance 2 apart. So a number p, which is prime, and the number p plus 2, which is also prime. So, for example, 3 and 5 is a twin, 7, 11, 13, 41, 43, and so forth. So given that Euclid's proof keeps generating all these twins, which are not divisible by any prime that you already have, it then becomes natural, although he never actually stated this in his work, but it still becomes natural to conjecture that just like there are infinitely many primes, maybe there are infinitely many twin primes. And because the proof of Euclid's theorem is so simple, maybe this should also have a very simple proof. But the amazing thing is that even after 2,000 years of research into primes, we still do not know the answer to this conjecture. We do not know whether there are infinitely many twin primes. Euclid's argument suggests maybe we should start multiplying some primes together and add or subtract 1, but it doesn't work. For example, if you add the first 4 primes together, 2, 3, 5, and 7, and you subtract 1, you get 209. It turns out not to be prime. It's not divisible by 2, 3, 5, or 7, but unfortunately it is divisible by 11 and 19. The largest known pair of twin primes is that thing written down there, 2,003,663,613 times 2 to the 195,000 plus or minus 1. Those twins are 58,000 digits long, and they were discovered this Monday. I read about it on the internet yesterday, actually, so I had to update my slides. The previous record was 51,000 digits long, so they beat the previous record by about 7,000 digits. So anyway, so that's that. Okay, so why are the primes so hard to understand? Basically, the thing is we don't understand the sequence of primes all that well. Here's the sequence of primes, 2, 3, 5, 7, 11. They behave, it's increasing, but other than that, they behave in a very sort of random manner, much more random than other sequences. So here's another sequence for comparison, the square numbers, 1, 4, 9, 16. That sequence is much more orderly because given any, I can tell you what the 1,000th element of what the 1,000th square number is without any thought. It's 1 million. The nth square number is n squared. But I can't tell you what the nth prime number is. Well, not easily. Okay, I can't tell you the 1,000th prime number without a lot of work. So the nth prime number is often called Pn. But we don't have a good formula for Pn. Well, other than P in itself, it's not a very good formula. But we don't have a useful formula for the nth prime. So the primes are doing. They're trying. There's only one prime sequence in the world. It's deterministic. It's not random, but somehow it seems to behave as if it was random in many ways. So there's a famous quote from Paul Erdős, one of the great mathematicians of the 20th century, referring to an earlier quote of Einstein. Einstein did not believe in the interpretation of quantum mechanics given by his colleagues because it seemed to imply that the universe had some randomness in it, and he said that God did not play dice with the universe. And then Paul, sort of riffing on that, said, well, God may not play with dice with the universe, but certainly something fun is going on with the prime numbers. Okay, so as I said, we don't have a good exact formula for the nth prime. Right? I cannot give you a nice formula for what P sub n is. But we do have an amazingly good inexact formula. If you're just willing to know what the nth prime is approximately, I can tell you with very high accuracy what the nth prime is approximately. And the big theorem here is something called the prime number theorem, which was proven over 100 years ago, that it says that the nth prime Pn is approximately n times log n. And this is not log base 10, which would be kind of weird since natural numbers don't care that we have 10 fingers. But it's log based on the natural log, e, 2.71828. Okay, so Pn is approximately n log n, and what approximately means is a precise meaning here, but I won't talk about that. So this is it's a funny theorem. It's really it's widely considered basically essentially the best theorem, the best achievement in number theory, the best single achievement in number theory probably. The proof is much more advanced than, it uses much more advanced mathematics than Euclid's proof. Euclid's proof, I gave you a complete proof. And it's a much deeper result. And the proof is really quite amazing. I'm going to give you a somewhat cheating, simplified version of it. But just to give you a taste of just how modern it is compared to what you just saw. So, and I'm going to use lots of imprecise terms. So what you do is that you analyze the primes as follows. So you have to create well, I call it a sound wave. Okay, the precise name is the von Weingold function. But create a sound which at prime times is noisy, at other times it's quiet. So at time 1 it's silent, at time 2 you make a noise, time 3 you make a noise, and then silent, 5 you make a noise, 6 silent, and so forth. Okay, so, and the volume of the noise, there's a formula for that. But so this is funny sound wave that you can make. It's a function. And you take this function and you listen to it. Okay, so the precise, what listen means is that you take a Fourier transform. Actually, you don't quite do that. You take what's called a Mellon transform, which is almost the same as a Fourier transform. So you listen to the sound wave, and you will hear certain notes. And you record the notes that you hear. And the notes have a name. The notes are called the zeros of the Riemann zeta function, which I will not talk about here. Colloquially, they're sometimes referred to as the music of the primes. And each such note refers to a certain, each note will give you some hidden pattern in the primes. If primes are oscillating at a certain frequency, then they will show up as one of these notes. And in principle, the entire distribution of the primes can be recovered from knowing what these notes are. And then what you do is that you show that of all the possible notes that could possibly show up in this sort of music of the primes, a whole bunch of them actually don't appear. And that's first tricky to state, but also tricky to prove. That's the hard bit, which I want to talk about here. But once you can exclude certain types of notes in this music, that tells you a lot about what that music does. And using that and either Fourier analysis or complex analysis, which is very related, you can then prove actually this prime number theorem. So that's, of course, so that was very sketchy, but that just sort of shows you just how modern this proof is. There are more elementary ways to prove the prime number theorem, but those proofs are longer and also not very intuitive. In fact, many people, yeah, they don't. The elementary proofs are not considered anywhere near as elegant or as informative as these much more modern proofs, these non-elementary proofs. So just to give you some example of the prime number theorem in action, the 1000th prime is 7,909. Whereas this n log n prediction is roughly 6,907. That's an error of about 13%. If you then look at the millionth prime or the billionth prime or the trillionth prime, the error slowly gets better, but it's not all that great. This approximation, you know, it's only good to one significant figure. But nevertheless, what the prime number theorem says is that as you keep going out in the prime sequence, the error will eventually go to 0. Okay, so in mathematics, you know, it's great to prove individual results, but often the techniques you use to prove those results are even more valuable than the results themselves because they can be then used to prove other things. So, for example, the techniques used to prove the prime number theorem can be used to prove many other statements, and I'll just give you 2 examples. So one is that if you take a large prime, any prime bigger than 5, actually, and you look at its last digit, you write it base 10, you look at its last digit, it's not hard to see that all large primes, the only possible last digits they can have is 1, 3, 7, or 9. There are no primes that end in 6, or 8, or 0, and only one prime that ends in 5 or 2. So all large primes end in 1, 3, 7, or 9. That's easy. But what's not so obvious is that those digits occur equally likely, that there are just as many primes ending in 1 as there are ending in 3, or 5, or, sorry, no, not 5, 1, 3, 7, or 9. 25% of all large primes end in 1, 25 end in 3, and so forth. That is not an obvious fact. And that took quite a while to actually prove. And there's a similar statement for other bases in base 10. Here's another famous theorem, Vinogrado's theorem from 1937, that all large odd numbers, any odd number that is large enough, you can write as the sum of 3 primes. So this theorem has a nice little history. It was conjectured by Goldbach, who was an amateur mathematician in the 18th century. So he, in fact, conjectured that all odd numbers larger than 5 are the sum of 3 odd primes, 3 primes. So, for example, 7 is 3 plus 2 plus 2, and so on and so forth. So, okay, so he conjectured that all odd numbers are the sum of 3 primes, and Vinogradov showed that all large odd numbers are the sum of 3 primes. Well, how large is large? Well, the barrier for what large means has been lowered over the years. The best result right now is from 2002. All numbers larger than 10 to the 1,346 all odd numbers larger than 10 to the 1,236 are known to be the sum of 3 odd primes. We also know that all numbers less than 10 to the 20 are the sum of 3 odd primes by a very different method. So that's the odd go-back conjecture. So presumably, this gap will close eventually. But you know, even with the best computers right now, there's no chance we can get up to 10 to 1,000 or so. That's more than the number of atoms in the universe. So that cannot be tested by brute force search. There is an even go-back conjecture, which is stronger than the odd go-back conjecture. It's conjectured that all even numbers larger than 2 are the sum of 2 primes, and this is still open. In fact, it's basically as hard as the twin prime conjecture. So that's still an open question. Okay, so the prime number theorem tells you approximately what the nth prime is. It's n log n. So there turns out to be a more accurate formula, or a formula that we believe to be more accurate, which is given by the Riemann hypothesis, which I won't state exactly, but one of its equivalent formulations is that it tells you a more precise formula, but a more complicated formula for the nth prime. The nth prime has to obey this funny equation, which I won't discuss more. This hypothesis is 150 years old, and one of the most important unsolved questions in number theory, so much so that the Clay Mathematics Institute in Boston has listed this as one of its 7 Clay Millennium Prize problems, and there's a $1 million prize attached if someone can actually prove this. Okay, and this will not mean anything if you don't actually know what the hypothesis is, but it's saying that this music of the primes is actually arranged like a chord, in some sense. But that is a very cryptic comment at this point. So just to illustrate how accurate this prediction is, here again is the 1,000th prime, millionth prime, billionth prime, and trillionth prime. And on the right-hand side, this is the prediction that the Riemann hypothesis gives, except for this error. There's a little error term in the Riemann hypothesis. So the Riemann hypothesis, even that doesn't predict what the nth prime is exactly, but it does give an astoundingly good approximation. So the 1,000th prime is only accurate to like 2%, but once you get up to, say, the trillionth prime, it's accurate to 0.0002%, the prediction by that formula. So it's a very good prediction for what the primes are. So the Riemann hypothesis, let me go back a little bit. So it's not an exact formula. It's got this funny big O thing, and I won't say what big O means, but this is just some weird error term that we don't understand. And this error term is actually the same type of error that you would get if the primes were somehow distributed randomly. If somehow God had managed to shuffle the numbers and sort of deal out the primes in some random fashion. In some sense, you would expect that the Riemann hypothesis type of prediction there to hold exactly this error due to something called the law of large numbers, which I'll not talk about here. So what the Riemann hypothesis is saying somehow is that the primes behave as if they were dealt randomly somehow among the integers. We call such things pseudo-random. They're not actually random, but they behave as if they're random. It's like the random number generators that are used in computers. They're not actually random. They come from some complicated algorithm, but they behave randomly. At least we believe so. So we would very much like to prove this Riemann hypothesis, which is a statement that primes behave randomly, but we're not very good at proving that things behave randomly. The problem is that maybe the primes look like they behave randomly, but maybe secretly after the trillionth prime, they all decide to maybe they take a big break. There's a big gap where there's no primes, and then they all bunch together. And we don't really know that the primes just sort of conspire to do something after a while that we can't see yet. And so, how do you show that conspiracies don't happen? That's it's a more philosophical question, but we don't really have good tools to prevent this from happening. Okay, so this is all pure mathematics, but this whole business about showing primes and things related to the primes are pseudo-random is not a purely academic concern. There are very many important things which underlie internet security or banking security these days, which rely on a belief that many things related to primes do behave as randomly as the mathematicians predict them to. And so, in many ways, trillions of dollars hang on certain beliefs about the primes, actually. And so just to give one example of this is something called the Diffie-Hellman key exchange protocol. This is a protocol invented in '76. And what it does is that if you have two strangers, which are traditionally called Alice and Bob, and Alice wants to tell Bob something secretly, but she can't. She can only communicate with Bob over an insecure network. She can only send emails through the internet, say, and this network is completely open. Everyone can read and can read every communication. If there's no secrecy, how can you still communicate some secret code? For example, some code number G, maybe the number to a bank account. How do you communicate this number from A to B without anyone in the middle, any eavesdropper, learning what that secret is, even though the network is completely open? So that's not obvious how to do it. If they weren't strangers, if they had previously met, they could arrange some secret code, but they have not met before. They can only talk to each other in a completely open way. So if they arrange a code, everyone hears them. So you can't just sort of try to set up a code that way. This is a digital problem, but you can think of a physical analogy. Imagine that Alice wants to mail, by physical mail, in an envelope, a message to Bob, but she knows that all her messages can be opened and read by people in the middle. So how can you still send secret messages when everyone can open all your mail? So you have to do a trick, and in the physical problem, here's the trick. It's a very cute algorithm. What Alice does, is that you take your message and you put it in a box, and you put a padlock on the box. Okay, and you keep the key, and you mail the locked box off to Bob. Okay. Now, so anyone opening the mail just sees a locked box, and they don't have a key. They can't open it. Of course, Bob doesn't have the key either, so he can't open it either. But what Bob does is that he puts his own lock on the box too. So now it has two locks. Okay, and mails it back to Alice. Okay, so now there's a double lock box coming back. Alice can't unlock Bob's lock, but she can unlock her own lock. Take it off. Okay, now only Bob's lock is left. Mail it back, and then Bob unlocks the lock again and gets back the message. Okay, so the eavesdropper never sees an unlocked box, and the Alice and Bob never have to communicate with each other, but they can transmit the message. So that's how you solve the physical problem. And the digital problem is done analogously. Math is all about analogies. And so, roughly speaking, if you want to send a secret number G, if Alice wants to send a secret number G to Bob, what you do is that you first agree on a large prime. You could pick any prime, that big prime I mentioned before you could use. So Alice picks a key, A, just her favorite number A, and she takes this message and she locks it. And the way you lock it mathematically is that you raise it to the power A. So you take G to the A, and then you have to take the remainder modulo P. But never mind that. So you lock it. You take G to the A, and you get a new number, and you send that locked number over to Bob. Bob can't decode that, but he picks his own number B, raises the G to the A again to B, and G to the A raised to the B is the same as G to the A times B. So now it's doubly locked, sends it back to Alice. Alice takes the 8th root of the number she got, and there's a way to do that, modulo P, which I won't talk about. And so that gets you back from GAB back to GB, and then she sends it back to Bob, and then she takes the B root of that, he takes the B root of that, and that gives back the G. Okay, it's the same algorithm that I described physically, but this is the sort of the mathematical analog. Okay, and this is believed to work. We don't actually have a proof that this is secure. If the eavesdropper actually sees all these secret numbers going back and forth, it might be possible that the eavesdropper could actually crack the code in some reasonable amount of time. We don't know that's true. We believe it's secure, but we have no proof. That's related to another one of the 7 Clay Millennium Prize problems, actually the P equals NP problem. If P equals NP was not, if P was, that's another whole other talk, but there's something called P, something called NP, and they're believed to be different. If they're equal, then we could do many things, in particular crack this code. In fact, we could crack any code, really, but in particular this one. We believe that P is not equal to NP, and we also believe that this code cannot be cracked. We don't know that's true, but we do have some data. there is a recent result I'm quite fond of, my friend Jean Bourgain, who shows that the data that the eavesdropper intercepts by this protocol, right? So an eavesdropper will see a whole bunch of numbers going whizzing past, usually A, usually B, usually AB. These numbers, what can be shown is that if you take the most significant digits of the numbers that you see, they are what's called uniformly distributed, which I won't define here, but it means that you can't distinguish them from they look like random noise in a certain sense. And you can't decode anything from random noise, other than more random noise. So that suggests that that the code is secure, but that's only the most significant digits. It doesn't. If the eavesdropper gets all the digits, then maybe he or she can decode the code. Quite fun of this result because it uses one of my own results from a few years back, but that's another story. Okay. Some disclaimers. What I described is not actually how Diffie-Hellman works. It's close, it's oversimplified, but that's a comment. Okay, only for experts. That's okay. There's a slightly different way to generate the secret, but that's it. The other disclaimer is that I mentioned two types of pseudo-randomness. So the Riemann hypothesis is one type of pseudo-randomness, properly concerning the primes, and the pseudo-randomness that is believed to make Diffie-Hellman secure is a slightly different type of pseudo-randomness. And they are, in some sense, similar in spirit, but they're not the same. Sometimes it's inaccurately reported that if you solve the Riemann hypothesis, you can start cracking codes, and that's not actually true. In fact, in many ways, if the Riemann hypothesis is true, it sort of lends belief to the fact that these codes are uncrackable. But there's no direct connection. They're just sort of spiritually connected rather than sort of directly connected. Okay. So my next topic is another part of prime number theory called sieve theory. So I've talked about how the primes behave somewhat randomly, but they're not completely random. There are some obvious patterns in the primes. Right? For instance, almost all the prime numbers are odd, with one exception. Almost all the prime numbers are adjacent to a multiple of 6. That's with 2 exceptions this time. That's a nice little result. And so on and so forth. So there are some obvious things that the primes do. I mean, basically, the primes cannot be divided by 2 or divided by 3 unless they are 2 or 3. And so that actually tells you something. There's a way to capture that very efficiently. It's a tool called sieve theory, and it's one of our basic tools for understanding the primes. So I just want to mention this because it connects with what I want to talk about. So sieves, the idea of sieves is, in some sense, you don't try to look at each prime separately, because that has proven to be very hard. You sort of view them in aggregate. It's like if you want to count how many grains of sand there are in a box. One grain at a time, that's very painful and not very fun. But what you can do is that you can just take your box of sand and weigh it, and then divide by the average weight of a grain. And that will give you at least a good approximation as to how many grains there are in your box. And so you can see that by treating things in aggregate rather than individually, you can do things more efficiently. And so the idea is to try to uncover the primes as a set in aggregate. The primes you can think of as some sort of sculpture buried inside the integers. So the natural numbers, 1, 2, 3, 4, 5, you can think of as some sort of maybe a block of granite. And what you're doing is you're trying to carve out the primes out of this block of granite. So what you do is that you take this big mallet and you're going to whack off big chunks off of this granite sculpture, and then after a while you take away your mallet and you take a chisel and you chisel off some smaller pieces, and then you put away your chisel, and then you take a needle and you make lots of little tiny fine adjustments, and then eventually you're going to get the primes. And this is sort of how sieves work. The most famous sieve, and the one that you may have learned in high school, is the sieve of Eratosthenes, which also dates back to 200 BC. And what it does is that given any n, like 1,000,000, you can get all the primes up to n, or actually all the primes between square root n and n, but actually all the primes up to n, as follows. So you take all the numbers from square root n to n, like all the numbers from 1,000 to 1,000,000. It's like this big block of granite. Okay, and then you just chop away half of them. You throw away all the even numbers, right, all gone. And then you throw away all the multiples of 3. You cross them off, and then multiples of 5, multiples of 7, multiples of 11, and so forth. You just keep well, it's a sieve. You keep, or you think of it as sort of sifting out the primes, or I like to think of it sort of as doing a sculpture. And so you keep making these changes again and again and again, all the way up to 1,000. So I think the largest prime that's in 1,000 is 997. So finally you take the multiples of 997, throw them out, and then at last, after all that, everybody that survives is a prime. And this is how you get all the primes from 1,000 to 1 million. Okay, so this is the standard sieve. For various reasons, it's not a very efficient sieve. There are more advanced sieves we use nowadays, which are much more complicated. It's more like, I don't know, it's more like a student application form. For, you assign numbers various scores or weights depending on various things. Like if you're multiple of 2, you lose some weight. If you're not multiple of 2, you gain some weight. And there are always weights that you add or subtract depending on various statistics. And then you finally have the score, and then if you're above a certain threshold or something, you gain admission, right? And then these are your primes. But that's a much more technical detail. So as I said, these sieves, they start off very simple. Like it's easy to understand what happens if I take a whole bunch of numbers and I throw away all the even numbers. I know what happens to the odd numbers. Okay, I have to throw away multiples of 2 and multiples of 3. What I have left is just everybody that's next to a multiple of 6. But then after a while, it gets very complicated, and we've never really managed to use sieves just by themselves to understand the primes. But what you can do with a sieve is that you can take the sieving process and just stop it halfway. And you don't quite, and if you stop the sieve halfway, then you don't throw out enough stuff. You get the primes, but you also get some extra stuff attached to the primes called the almost primes. Almost primes are numbers which are not prime, which may not be prime themselves, but have very few prime factors. Maybe numbers that only have 2 or 3 prime factors. And what sieves have done for us is that basically, roughly speaking, while we don't understand the primes so well, we do understand the almost primes quite well. So just a very typical result here, something called Chen's theorem, which is, so you remember the twin prime conjecture. There should be infinitely many primes, P, where P plus 2 is also prime. We don't know that yet. I would dearly love to see that proven. But this is the newest we've got so far, which is that there are infinitely many primes P, where P plus 2 is either a prime or a product of 2 primes. So it's sort of, it's almost the twin prime conjecture, but that's the best we can do. That's basically the limit of sieve theory in many ways. We know in some sense that sieve theory cannot do much better than this theorem. Okay, so finally I can talk about my own work. So as I said, even after 2,000 years, we can't detect many patterns in the primes. I do not know how to find lots and lots of twins in the primes. There are lots of other things I don't know how to do, or no one knows how to do. You know, we don't know how to write large even numbers as a sum of two primes. But there is one type of pattern that we can actually do something of, because there's a cheat available for one type of pattern, arithmetic progression. An arithmetic progression is a sequence of numbers which are equally spaced. Every number is the same spacing from the previous one. And my theorem of Ben that I proved 2 years ago, Ben Green, is that the primes, inside the primes somewhere, there exist arithmetic progressions of arbitrary length. So somewhere in the primes there are progressions of length 1 million. Somewhere in the primes there's a progression of length 1 billion. I can't tell you exactly where they are, but I can tell you that just like Euclid's theorem, I can't tell you exactly where these progressions are, but I can tell you that they can get as long as you please, and also there's infinitely many of them. So as a consequence, given any k, not only can you find a progression of length k, but in fact you can actually find infinitely many progressions of length k. Okay, so this builds upon a number of earlier results. For example, it was known before that you could find progressions of primes of length 3, but now we can find progressions of primes of any length at all. So just to give you some progressions of primes, here are the first few progressions of primes of each length. So the first progression of length 1 is 2. The first progression of length 2 is 2 and 3. The first progression of primes of length 3 is 3, 5, and 7, and so forth. So the first few progressions look fairly small, and you would think that it's easy to find the next few progressions in sequence. Actually, already finding the first progression of length 7 is not easy, and I haven't written it down here. What's the longest progression of primes that we know of? the longest explicit progression of primes that we know of has length 23. Okay, we have an example of a progression, arithmetic progression of primes of length 23, just 23. That's all. But already these primes are this is 56 trillion, and the spacing is 44 trillion. Yeah, of course you need a computer to find these. We don't know of an explicit progression of length 24. But nevertheless, we have shown that somewhere out there is a progression of 24, and 25, and 26. There's absolutely no chance I can tell you about how this is proven, except, well, so I'll give something which maybe is not so enlightening, but the 1 second soundbite, 1 minute soundbite, is okay. So sieve theory that I mentioned before. That allows you to tell, it doesn't tell you that the primes contain long progressions, but what it can tell you eventually is that the almost primes contain long progressions. So you can find lots and lots of really long progressions which are not prime, but they're almost prime. So what does that tell you about the primes? Well, the primes are a subset of the almost primes, so they're somewhere in the primes and the almost primes. But we don't know how they're distributed. Maybe they're distributed in a very uniform, spread out manner. Maybe they're distributed in a very structured sort of manner. We don't know. We still don't know. We're working on it, but we still don't know exactly how they're distributed. But what we managed to do, what Ben Green and I managed to do, is by 2 different arguments, we could show that regardless of whether the primes are structured or random inside the almost primes, it doesn't matter which one, regardless of how they're distributed, in either case, they must necessarily contain arithmetic. They have to contain a fraction of the progressions that their parent set, the almost primes, do as well. That the arithmetic progressions have some sort of hereditary property, that if one set has got lots and lots of progressions, then lots of subsets will also have lots and lots of progressions. There's some weird hereditary property which is special to arithmetic progressions, and it's not true for, say, twins. This method does not give the twin prime conjecture, but for some reason progressions have a special property that you can pass to subsets and you still keep a lot of progressions. But that's a whole long story. Anyway. So just to finish up, we have a lot of work still left to do. As I said, our theorem doesn't tell you exactly where to find, say, the first progression of length 1 million. It does give you a bound, as it turns out. We can tell you that if you want to find the first progression of primes of length k, we can guarantee you that that progression will exist, and not only that, that all its entries will be less than 2 to the 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 2 to 100k. That's what our argument gives us. That's not what the truth should be. The conjecture is more like k to the k, so 1 exponential. This is 7 exponentials. There's several inefficiencies in our proof that we have to resolve. But just to connect with a previous thing, this Riemann hypothesis that we say we can't solve, if that's true, we can get rid of one of the exponentials in our bound. But not the rest, unfortunately. Anyway, that's a good place to start. Thank you very much.
Do you use computers in your work?
I personally don't. All the various records that I listed up there were done by computers, but I work on more the theoretical side of things. I do not myself use computers. Well, other than, of course, to do something. Yes.
Do any of these results work for the Gaussian integers and the Gaussian primes?
Yes. So, for example, I have a paper from a couple of years ago that there's an analogous theorem for the Gaussian primes. So the Gaussian primes are arranged in a grid rather than on a line. And the analogous theorem is not that they contain long progressions, but they contain constellations of any given shape. There's a movie called A Beautiful Mind, where at one point the protagonist, who's Russell Crowe, wants to impress his girlfriend. So he challenges his girlfriend to name a shape. I think he an umbrella. And then he looks up in the night sky, and after a while he finds a bunch of stars arranged like an umbrella. So the Gaussian primes have the same property. If you give me a shape, like an umbrella, eventually somewhere there's some arrangement of Gaussian primes that is shaped like that umbrella. They use the same method, actually. Yeah.
Do you by chance know how the largest prime number was found?
Yeah, so that particular number is, you may observe that it's almost a power of 2. It's what's called a Mersenne prime. There it is. And for numbers that are close to numbers that are close to a pure power, like a power of 2, there is a special way to test for primality, to test whether something is prime or not. And that's yeah. So most numbers that are 9 million digits long, even the fastest computers cannot tell whether they're prime or not. But these special numbers, the special methods, number field sieves and so forth. It's not a subject that I know that much about. But, yeah. Possibly. So there are 7 Clay prize problems and one's been proven right now, the point Clay conjecture. The Riemann hypothesis, I think, will be somewhere around the second to last to be proven, I think. P equals NP will be the last, I think. But yeah, it's possible. But I think someone will have to stumble across something unexpected. I mean, you can't solve it just by using all the known technology. You have to discover something that hasn't been discovered before. But, yeah. But it might happen. I mean, we didn't expect the point Gray to be proven until it was. So.
What's the most compelling unsolved mathematical problem in your?
I don't know. Everyone has their own favorite. Well, there's a sort of you want problems that are compelling, but also have some chance of being solved. I mean, so there's, I mean, I myself I'm fond of problems that just look barely out of reach. You just need to do a little bit of stretching to reach them. I mean, these big, really famous problems, they're very frustrating to work on directly. While it's great to know about these, you shouldn't spend too much time on devoted entirely to those, and actually, do something more within reach. So, I don't know. Yeah. There are many. I mean, there are thousands of unsolved problems listed in the literature, and we don't just work on the big ones. Yeah, that's in fact, we almost never work on the big ones actually, because we can't do them.
There's one final little ceremony, which we present Terence Tao basically with what's called the Dean's Recognition Award, but it's really a certificate of appreciation for coming and talking with us. On behalf of everybody, I'd like to thank you again.
Okay.